excited to be able to share with you all this work. Yep, this is work here on probabilistic PCA for heterogeneous quality data. So we'll see exactly what we mean by all of this. And this is joint work with Kyle Gilman, Laura Bolzano, and Jeff Fessler, all at Michigan. And I've included here the DOI at the bottom, if you'd like to pull up the paper and follow along or look up some of the details. So yeah, let's see. So I think I mentioned this earlier. I don't know if more people have joined since then, but please feel free to interrupt me. You'll see I prepared about 21 slides, and I'm hoping for some of them that we can engage on them and discuss. So I'm looking forward to that. So please feel free to interrupt with questions and comments. And then secondly, if someone drops in the chat a comment that I miss, please feel free to also call that out for me. So yeah, without further ado, there we go. So the kind of motivation for this work is that big data is often heterogeneous data. And so a lot of modern data sets contain data of varying quality. And so kind of an illustration of that, or kind of a toy stylized example of that, is you can imagine, you know, in a city, for example, let's say we've got a bunch of sensors here, kind of as an illustration. I'm imagining thermostats placed all around the city. And you might have a few high quality ones, which are maybe like government maintained instruments. And then you might also have, so only a few of those because they're very expensive. And at the same time, you might have a lot of really inexpensive sensors, maybe household ones that are scattered throughout the city. They're all measuring the same underlying phenomenon, but the measurements from the high quality sensors is going to be less noisy than the measurements from the low quality sensors, even though kind of they all have the same, maybe it gets warmer during the day and then gets cooler in the evening. All right, so this is kind of the picture we have in mind, right? We've got a bunch of different sensors measuring the same phenomenon. Some of them are higher quality, less noisy. Some of them are lower quality, more noisy. Okay, and typically it'll be costly. The higher quality ones will also be more. Okay, so there's all sorts of settings where this comes up. So actually, an original setting that motivated our work was medical imaging, and in that context here, you're looking at a CT machine. And in X-ray CT, what happens is that from patient to patient, they might change the radiation level, and essentially a higher radiation level corresponds to a higher SNR. And you've got maybe data sets that have got lots of images taken over long periods of time at varying radiation levels, and you'd like to do some kind of overall analysis of them. A second one here in the middle is coming from astronomy. So in some of our other work, we've looked at some data from the Sloan Digital Sky Survey, which is this huge survey of the night sky. And due to a variety of different effects, including, for example, a varying atmosphere, some of their measurements are more noisy than other measurements. And then finally, we've also looked at air quality data, and so there's in the U.S., for example, there's the EPA, the Environmental Protection Agency, maintains high quality instruments at different locations in the U.S. to measure air quality. But there's also a company called Purple Air, which sells a consumer grade air quality sensor. That people can buy and put all over the place in the U.S. So there's many of those, but the measurements from those are less are more noisy. Okay, so due to all these kind of effects in all these different settings, I know there's a number of people here in the audience who are experts on radar, and as I understand in radar, there can be heterogeneity due to heterogeneous levels of clutter, and so this is kind of a ubiquitous, I think, setting. Now, in all these settings, another common feature is that these are all high-dimensional data sets. So, for example, in the medical imaging case, you've got millions of voxels, maybe thousands of pixels for the sky surveys, thousands of locations for the sensors. But we anticipate that there's some kind of low-dimensional structure. And in the radar context, I think it'd be low-dimensional clutter, is my understanding. And so a standard and, one might wonder, maybe well understood tool is principal component analysis. And so the question here, the sort of overarching question is, how should we account for heterogeneity when we do PCA? Okay, so again, principal component analysis is going to be a way for us to try to identify the low dimensional structure in high dimensions. Now I'm going to be kind of framing things in terms of PCA, but throughout the talk, you can also think about this essentially as a low rank estimation problem, where we're trying to seek a low rank structure in high dimensional data. So this is actually quite a growing area, and so it's very exciting to sort of be working on this. And so myself with some collaborators, we've done a variety of works in, for example, asymptotic analysis of PCA for heterogeneous noise across samples. So in other words, you can ask the question, when the quality is heterogeneous, when there's heterogeneous levels of noise, what happens to the performance of PCA? Here today, we're talking about this probabilistic PCA. We call it HePPCAT, is the name of the method. Now, I know within folks here, there have been a number of works on the problem of heterogeneous signal strength. So this is where the noise is homogeneous across samples, but the signal strength is heterogeneous. Now, in both of our contexts, the heterogeneity is coming across the samples. So different samples have different levels of noise or different amounts of signal. But there's also another line of work where people have looked at heterogeneous noise across features, so across the other dimension of our data. And then there's also questions of how do you choose the rank. And so one thing, I'm realizing I forgot to include on this slide is that along the lines of this asymptotic analysis, we've also studied a weighted PCA approach, which is also a very natural approach. And so yep, I'd be happy to talk about that afterwards or another time. So, but yeah, this is, I think, just an exciting area, and it's an important problem. So today, our focus is going to be on PCA with heterogeneous quality samples. Okay, and so more precisely, we're going to imagine there are a data set. I'm going to denote it by matrix Y, which is D by N. Okay, so we have D features and samples, or we have D-dimensional data, and we have N samples of them. We're going to imagine that it's made of L blocks of samples. So where each block here is going to be, that's sort of where the heterogeneous quality comes from. So for example, if we had L different sensors, that's what you could imagine here as being the blocks. And so let me start with this picture on the right first, because that really conveys the main idea. So this green line is showing the underlying low dimensional structure. Okay, so the underlying low rank structure is in green. And we're going to imagine that basically data is drawn from this line, and then noise is added to it. And so the dots here, the samples in the blue block here, have a noise variance of 0.1. And the red dots here have a noise variance of 1.9. So so basically you have two blocks of data, the blue and the red. The blue is less noisy than the red. Okay, but we're given this data all together. All right, now more specifically, how do we model this? Well, we're going to have the Lth block is going to have a low rank part, low rank signal part, plus a noise part. And the low rank signal part is made of a factor matrix. You see D by K. So this is the low dimensionality here. The latent dimensionality or the intrinsic dimensionality here is K. Okay, so we got D by K so-called factor matrix. And we're going to multiply to that coefficients, ZL, which are just IID, Gaussian 0, 1. For the purpose of everything, just for simplicity today, I'm going to do everything over the reals, but everything extends to be over the complex numbers as well, in which case this would be complex normal, spherically symmetric. Okay, now the noise has IID Gaussian entries, but now the variance is VL. And so you see the index L here means that different blocks can have different noise variances. But notice that the factor matrix is common across all of them. Okay, so again, this is sort of a situation where we have a common underlying phenomenon that we observe through different levels of noise. Okay. Equivalently, the ith sample in the lth block is just Gaussian with mean 0 and covariance FF transpose plus VL identity. Okay, and so here you can see this is the low rank signal covariant part of the covariance. This is the noise part of the covariance. Okay, and the problem is to estimate the factor matrix F and the noise variances V1 through VL, given the data Y. So, okay, this is the problem. So now, natural approach is to do what's sometimes called probabilistic PCA, or in other words, maximum likelihood estimation, right? So recall here is our model. The ith sample in the lth block is again mean 0 with covariance having a signal component FF transpose plus a noise component VL ID. Okay, and so we could write down the log likelihood, dropping the constants as we usually do, and it looks like this. Okay, so let's take a moment and look at this. So generally speaking, we've got here a log determinant term, right? So this is coming from the determinant term of the Gaussian PDF. And then here we've got a trace term, which is basically like which we might often rewrite as something like, YL, which sometimes gets written as a Frobenius norm. So here, what you can see though is that F basically appears in both the log determinant term and this term, as does V. Okay, and so now now we have big L of these terms added together, and now for each of those terms we have a different VL, different YL, same F. Okay. Very good. So now in the homogeneous case, so that's when L, you can think of a homogeneous case as basically just having one block. And in that case, what's known is that actually this MLE is given by, or in other words, the maximizer of this objective is given by eigendecomposition of the sample covariance matrix, and then with some shrinkage applied to that on the eigenvalues. And so essentially what you can imagine here is that when you've only got one of these terms, notice that you can move the YL over here on the right. Okay, great. So you can move this YL over here in the trace to the front, and now you see you essentially have a sample covariance term. And since there's only one of them, this sort of everything factors nicely, and you can solve this basically by eigendecomposition. And then there's some shrinkage just due to this, the log determinant term. Okay. But now the new challenge for us in this work is to handle the case when L is greater than 1, because in that case, actually seemingly not solved by the singular value decomposition or eigendecomposition, because once you have all these L terms, the way they interact, basically, things don't separate nicely. Moreover, we're trying to estimate that's even further complicated by the fact that F and V have a bit of a complicated relationship to each other, right? You can't really separate the problem into just F or just V. You have to deal with them kind of together. And so the overall kind of high-level approach is a natural one, is basically to do block coordinate ascent. We're going to do an update with respect to F and then an update with respect to V. In other words, we're going to do an alternating maximization. Yeah. Okay. So yeah, so how do we do this maximization? Well, I'm going to basically, so the kind of next few slides, I'm going to kind of walk through the update that we do for the factor matrix F, and the update we do for the noise variances V. Okay, so again, our goal is to maximize this function, okay, of F and V. Okay. So for the F update, what we're going to do is we fix V at VT, and we're going to maximize this with respect to F. Okay, and so here, so here, in other words, what we do is we're taking the log likelihood. We're going to plug in, let's say, the current estimate of V. Let's call it VT. We're going to plug it in right here. and we're going to try to maximize with respect to f. Okay, and so here's what that objective function looks like. Excuse me. And here you see that basically f still appears kind of in a complicated way. And so it's actually not that straightforward how one would solve this, for example, in closed form. And so we're going to use a somewhat natural approach for these kinds of problems, which is expectation maximization. And if you're familiar with expectation maximization, we're going to be using a so-called complete data log likelihood, where the complete data is going to be YL and ZL. And so in other words, kind of in general, the approach is you write down a log likelihood for where you imagine that your data was not just YL, but it was both YL and ZL. So in that case, the log likelihood would look like this. All right, remember that YL was, if you're given, if you know F and ZL, then YL is just Gaussian with respect to that. And then is just Gaussian with mean F times ZL and variance VL coming from the noise. And then here's the term for just the ZL, which is just Gaussian with mean 0, variance 1. Okay. Okay. And now we take an E step, which is the expectation step. So in that step, you take an expectation of the complete data log likelihood with respect to this conditional probability of ZL given Y, the current estimate of F and the current estimate of V. And this basically gives us a minorizer. So EM can also be thought of as a majorize-minorize strategy, where the E step is a way of obtaining a particular minorizer for the function. And so here it looks a little complicated, but you just kind of do all the algebra and you get this expression where M and Z are these things. And the main thing to note about M and Z is that that they can just be computed based on the current estimate of F, the current estimate of V, and the data. Okay. And so our goal is to so we're going to think of this mainly as a function in F. And then the M step is going to be to maximize this with respect to F. And if we look at this, one might at first think that this looks very similar to what we had before with the original log likelihood. But the key is that before we had this VL, which is also a variable, number one, and number two, it kind of appeared in multiple places in a bit of a complicated way. But here now things appear in a kind of a simpler way, and we can just solve this for F. Maximize this with respect to F, obtaining this sort of closed form thing. If you look at this is sort of maybe what generally you might expect, given that this is sort of a quadratic problem in F, and so this looks kind of like a least squares type solution. Great questions. So this is the F update, and as you can kind of see, it's sort of a standard approach of EM, and sort of relatively straightforward to go through the steps. And so here is basically the update at the end we get, and this can be computed fairly efficiently. And so this ends up not being a bottleneck in the algorithm runtime. So now, with the F step complete, I'm gonna move to the V update. So now we're going to fix the factor matrix. Again, this is the low rank signal, which is common to all the blocks. And now we're going to try to update our estimate of the noise variances. Right? So we're going to maximize with respect to V. So that problem looks like this. Okay, if we plug in FT for F, and now we maximize with respect to V. Now, the thing you might observe is that this actually separates into L univariate maximizations of something that looks like this. So the first thing to note, for example, is that this sum over L, each of the terms are totally independent, right? V1 only appears in the first term, V2 only appears in the second term, and so on. So you can consider one block at a time now. And then if you look at one single block and do some algebra, basically, it turns out that you can just write this in this form. So sum over J of some alpha, some coefficient, times a natural log of some another kind of term, plus VL plus a sort of 1 over V kind of term, okay? Now, the particular values of these for alpha 0 and beta 0 are going to be this. Gamma 0 is 0. And then for j greater than or equal to 1, so j from 1 to k, alpha j is 1, beta j is this, gamma j is this. And in particular, these u's and lambdas here are the eigenvectors and eigenvalues of f transpose. So again, f was our is the factor matrix. Ft is the current estimate of that factor matrix. So ft transpose is the current estimate of the low rank signal covariance. Okay, and these are the eigenvectors and eigenvalues. So we just write it this way because it's a little bit convenient to write in terms of the eigenvectors and eigenvalues of ft transpose. Okay, so basically we have now this univariate problem to solve. And a kind of interesting thing is it turns out that, for example, when the number of blocks is sort of sufficiently large, I know in some of the radar contexts, for example, like each sample has its own signal strength. And so in that kind of a context, in that kind of a setting, this step can actually be quite expensive, even compared to the F update, which personally actually was very surprising. I really thought, oh, the F update is going to be an expensive thing, but it turned out the V update actually was kind of the expensive part. And it's because you're just doing so many of these sort of univariate maximizations, and each one can be kind of costly. So let me go into now, for this one, we actually investigated and we considered and came up with actually a variety of approaches trying to basically make this this part faster. And so I'm going to go through these 5 approaches now. I think given the time, we won't be able to go into all of them in detail, but I'm going to go into a little bit of detail, at least for the first few, and then for the last 2, I'm going to refer to the paper. Okay, let's jump in. So here's the first approach, which is just to say, hey, this is a univariate problem. Well, maybe we could even just do global maximization. And so in particular, if we differentiate with respect to VL, well, in the generic case, we end up with this this derivative, okay? And so this has got like, some kind of, basically it's a rational function in VL. And so certainly you can imagine that, we could, for example, clear the denominator, and then we have a polynomial in VL, which we could solve. Another approach here is to basically observe that for each of these terms, for each summand, basically when VL is when VL is to the left of beta j over alpha j minus gamma j, then this thing is going to be positive, and it's going to be negative to the right. Okay, and as a result, what we can say is that, well, if you're sort of sufficiently left, we know that this is going to be positive, strictly positive. And if you're sufficiently right, we know there's going to be negative. And we can calculate, sort of what we mean by sufficiently positive or sufficiently to the left and sufficiently to the right. Excuse me. And so now, as a result, all the non-negative critical points of this of the objective, have to occur within this interval. Okay. And keep in mind, again, that we only are interested in the non-negative critical points because the VLs, the variances here, have to be non-negative. So this is a good candidate for a method, kind of a technique called interval root finding. And so we sort of use an off-the-shelf interval root finding package to find, what it's able to do is it's able to actually find all of the critical points. And what we can then do is once we find all the critical points, we can evaluate them and choose the global maximum. Okay, so the first approach is global maximization with some sort of careful use of interval root finding methods. Okay. Second approach is to do expectation maximization. And so after some algebra that I will spare you from, it amounts to maximizing something that looks like this. Okay, so something like natural log VL minus something over VL. Okay, and so where that rho TL looks like this. If you sort of squint at it, if you look at it, it sort of has a flavor of a residual term. And But if we look at this objective, it's simple to solve. The solution is simply this, rho TL over D. Okay, and so this one is really clean and elegant, very simple. Okay, but of course here we're not doing global maximization. We're not doing a complete maximization with respect to V. We're just doing an EM step. Okay. Yeah, actually, yeah, okay. And then now the third approach is to observe that this is actually a concave plus convex objective, also called a difference of concave objective function. And so one of the standard approaches for handling difference of concave functions is to minorize the convex term with an affine function. And so here we've done that. We're going to minorize this. We're going to minorize this negative natural log with here this affine function. Okay, and we're minorizing at the current point VTL. So strict concavity in the generic case of this function now means that there's only one maximizer. And so we could do, for example, bisection to find it. And just like in the global maximization context, we're able to derive like a bound for where that where the critical point should be. And so so we can just use that initial interval, do bisection, and find the critical point. Okay. And then now the last two approaches, which I won't go into as much, are a quadratic solvable and a cubic solvable minorizer. And essentially here, what we've done is we've taken the different terms, we've sort of carefully exploited some of the structure and sort of minorized different parts of them. I can go into more detail later to obtain, in the first case, something that can be solved by basically taking the root of a quadratic polynomial, which we of course have in closed form. And then in the cubic solvable case, it's a slightly tighter minorizer, potentially, at least potentially a slightly tighter minorizer. But it results in solving a cubic polynomial, which we can also do in closed form, though the formula is, of course, more complicated. So these are the kind of 5 approaches we consider for the V update. And of course, there are many other approaches one could consider. But you know, we felt these 5 were kind of a good kind of sampling of different kinds of perspectives, one might say, on how one might think about solving this, right? They sort of take different, they kind of view the problem from different lenses and give 5 different approaches. Okay, so actually, maybe for a little bit of interaction, I'm curious. I can flip back and forth. I'm curious if people have any intuition about what they might expect to be the fastest among these approaches, among these 5 approaches. Now, the one thing I want to point out is that if you compute and we have this in the paper, but basically the complexity of all of these updates is the same. And so from the standpoint of complexity, you know, one might say, oh, the per iteration cost is equal. But it turns out, of course, that the actual runtime can be quite different. Basically, the constant can be quite different in the computational cost. Okay, so without further ado, let me show you the answer. So here, so we're asking which method is the fastest, and what we're looking at here on the left is the the convergence with respect to the objective function versus wall time. And then on the right here, we're looking at convergence of the factor matrix estimates. So just to point out here, what we're looking at is not just fix V, update V, fix F, update V multiple times. We're looking at basically the alternation, but where we're using different choices of the V update, right? So, I mean, another complicating factor here is, well, one might wonder, okay, if I do a better job of optimizing with respect to V in this step, maybe that will help me in the F update, right? Or maybe it doesn't help me, right? So this is sort of a thing we're trying to investigate, is how does all of this stuff, when you put it all together, play out? And so here we've got global maximization in black, difference of concave in blue, cubic solvable in orange, EM in green, and the quadratic solvable in purple. And a couple of things we can observe immediately is that the global maximization indeed, oh, sorry, I should point out here, we're looking at, again, There's convergence of the objective function versus wall time, convergence of the log likelihood compared to wall time. And then each of the dots here is one of the iterations, okay? And so going from here to the first point, you can see that global maximization really has the biggest jump, as you'd expect, because it's actually fully optimizing the objective. Interestingly, the difference of concave one is making a much smaller step, actually, while the rest of them seem to do pretty similarly, okay? But overall, we can see that maybe as one might have expected, global maximization does a really good job in terms of per iteration descent. But when you compare against wall time, it's quite a bit slower than the other methods because the per iteration cost is high. So indeed, actually, that interval root finding method is an iterative method on its own. It doesn't have increasing complexity in the data size, but it can be quite costly. And you can see EM as a couple of us voted here is doing quite well. And I think these three methods down here, you can't even see the cubic solvable one because it's buried inside. I mean, the differences are basically in the experimental noise, I think, at this point. So great. And basically, we see kind of the same things happening in terms of factor matrix quality. Okay, but this what I'm showing right now is for a case where the data is actually homogeneous quality. So there's a case where I'm pretending that I'm running the algorithm as if the data is heterogeneous quality, but actually the data I passed in is actually homogeneous quality. So now in this case, we can ask and look at, well, why do they perform the way they do? And here what I'm showing is the minorizer. What I'm showing here is the minorizer evaluated at the initialization. So here we're looking at the minorizers for V1 and here I might have a small error in terms of the graph. I'm sorry. This should be V2. Yeah, and so here in black is the actual objective function, and here you can see all the different minorizers. And in blue here is a difference of concave, and you can see that this all the other minorizers essentially match the objective function, but the blue minorizer, the difference of concave minorizer doesn't, and that's part of the reason why we see slower convergence there. Okay, now what if the data is actually heterogeneous though? So now here we see a little bit more interesting changes. And so similar stuff at first, that the global maximization is the slowest method because of the per iteration cost is high. And you can see in some sense, actually, the per iteration cost has grown even. And that's because since we're heterogeneous, the noise variance estimates need to change more. And so there's more work to do in the noise variance update. So this global maximization is quite expensive. And then actually a lot of the rest of them are kind of similar now in the heterogeneous case. And now, of course, the question becomes sort of which of these would you do? And here I think actually EM is one of the best options, turns out. So this is actually quite surprising. We had developed some of this cubic solvable, quadratic solvable minorizers, hoping actually that this would improve upon EM. But when we actually tried it out, it seems to be actually quite similar. So, this was, I think, quite revealing and yeah, it was really interesting to see, because this is something that we, in some sense, could not have maybe really anticipated before we tried it. And yeah, if people have thoughts on this, I'm happy to discuss more after. But let me quickly show here the corresponding minorizers. This is quite interesting. So here again in black is the actual objective function. And I apologize, there's a typo in my slide, so I'm actually missing the one for V2. So, but it's essentially a similar story. So let's focus here just on V1. And the black here is the objective function. Here I'm showing at this point here, this black dot is the current estimate. And then these are all the different minorizers. So as minorizers should, they all coincide at this point. And then they are all lower bounds for the objective function elsewhere. And so in blue here is the difference of concave. And you can see this minorizer is quite loose, actually more so than initially expected. But in hindsight, maybe it makes sense because essentially what we did is we minorize this natural log term by an affine term, and that's quite a strong kind of relaxation. Now, if we zoom in here, you can see that all of these guys are quite close to the actual objective function, and indeed also their maximizers are quite close to the actual maximizer, which is over here. Okay. So this kind of provides an explanation for why all those methods seem to have similar per iteration descent. And given that their sort of relative costs are kind of similar, it kind of makes sense that their speeds would be somewhat similar. But now in terms of, which one might I recommend? Actually, in our paper, we recommend one of the methods that we recommend is EM, partly because it's quite simple to implement, and it seems to do quite a good job of actually, it seems to be quite a tight minorizer. Okay, so let me conclude here by going through now. So we've been talking mostly about the challenge sort of actually computing the maximum likelihood estimate, right? But of course, we'd like to maybe see how it performs in terms of statistical performance, or in terms of sort of the estimation performance. And so here, we're going to do a comparison with a variety of other methods. And here, what I'm showing, let's see, given the, in the interest of time, let's focus mainly on these leftmost figures. What I'm showing in all of them actually is a case where you've got two blocks of data, and the second block is becoming increasingly noisy as we sweep across. So sigma 2 here is the standard deviation of the noise standard deviation for the second block of data. But the first block of data has a fixed amount of noise, okay? But the second block getting noisier as we go to the right. And here we're looking at the estimation error of the factor matrix. And here essentially you see HePPCAT, which is in blue, has the lowest estimation error out of all of these options. What are the other options? In pink here is what if you just did a homoscedastic probabilistic PCA? So if you sort of pretend the data is homogeneous, that's in pink. You just plug it in. So certainly, as that second block of data gets more and more noisy, the data is becoming more and more heterogeneous, less and less homogeneous, then the error grows. In green here is the performance of doing homoscedastic PPCA, but only on the first group where actually the data is homogeneous. So in other words, you throw away the second block of data, second group of data, you only use the first group. And then in yellow, same thing, only use the second group, throw away the first group. And so, indeed, you can see here for homoscedastic PPCA, once the second block gets noisy enough, it's actually better just to throw away that second block and just do PCA on the first block, right? But what does HePPCAT do? HePPCAT sort of combines everything carefully so that it sort of performs as well as you could with any of these other methods across the whole range. Here, I'm looking at basically the recovery of the eigenvectors of the factor matrix, of the factor covariance, and basically it's the same phenomenon you see here. Okay, and then this bottom set of plots is comparing HePPCAT with sort of weighted PCA variants or some other kind of variants that are tailored more towards trying to do something for the heterogeneous noise. And so kind of the story here, the takeaway here is that HePPCAT generally seems to match or sort of outperform these different methods, and it sort of does a careful thing in some regimes it sort of matches the inverse noise variance, so-called weighted PCA, and some other regimes it matches something called square inverse noise variance weighted PCA. But kind of the main takeaway here is that HePPCAT sort of carefully is combining again the data, and it's sort of combining the data in an appropriate way and appropriately accounting for the heterogeneity. I won't talk about this too much. This heteroPCA method is actually a method designed for, is primarily designed for feature-wise heterogeneity, so not the sample-wise heterogeneity that we're interested in, and that's why it doesn't perform very well. Okay, and let's see. So the last thing I wanted to share with you all is, we might also ask how well are the noise variances estimated, and how does that impact the the estimate of the factor matrix. And so here, what I'm showing is the noise variance is estimated from one instance of data. And here, so in this case, the first 200 samples had a noise variance of 1, and the latter 800 samples had a noise variance of 4. Okay, so the first 200 samples less noisy, the last 800 samples more noisy. And if we, so we could run HePPCAT, our method, with these two blocks of data. But in some cases, maybe you don't know actually what the blocks are. So you can imagine that you actually told HePPCAT, you provide the data to HePPCAT in blocks of 100. So you gave the first 100 points samples as one block, the second 100 samples as another block, and so on. And this is basically showing the estimates you get. And we go all the way down to a block size of 1, meaning we are trying to estimate a separate noise variance for every sample. And you can see in these blue dots are all the different noise variance estimates. And you can see they indeed roughly end up clustering around 1 and 4. And then if we look at a mean interquartile intervals doing 100 data realizations, so these are 100 data instances, because indeed, as pointed out before, the data is random, then we end up sort of getting these kinds of interquartile ranges. And what's interesting here, I think, is that, for example, one could imagine even treating everything as a block size of 1, and the variances cluster. And so if you try to cluster them afterwards, you could do that, for example, as a way of cleaning things up. And but generally, we see that even for a block size of 1, actually things seem to be pretty well behaved, and we can actually get pretty good estimates of them, of the noise variances. And this bottom graph is just showing what happens to the corresponding factor estimate. And an interesting thing here is that if you look at these three curves, you can't really tell them apart. Again, I think this one is looking at, again, 100 data. I think it's 100 data realizations. And an interesting thing here is, again, even if we treat all the samples as having separate noise variances, actually the quality of the factor matrix, which is often what we're most interested in, is basically the same. So this kind of means that the method is quite robust, actually, to the choice of the number of blocks and how the data is basically divided up. And you can even just say, treat all the samples as being their own block, which is the most general. It's imposing the least assumptions. Of course, if you impose more assumptions, you can basically get higher quality estimates. But at the risk of maybe being wrong about those assumptions. So yeah, I think this is quite remarkable to see that some of these results quite surprised us quite a bit, because man, the method was much more robust to these different sort of choices than we expected. We really thought that if you choose a block size of 1, that, oh man, maybe this problem is not even really well posed, and or maybe it's very ill conditioned, and maybe things will be will perform very poorly. But yeah, it seems to be performing quite well. And here we can discuss more afterwards, but I think the high dimensionality helps. So let me conclude here. So today we talked about how big data is often heterogeneous quality, which requires new methods, and that probabilistic PCA for heterogeneous quality is a challenging optimization problem that can be tackled via alternating maximization, and with some interesting challenges in the V update. And we saw kind of how those different choices and algorithmic choices change and impact the performance in terms of runtime. And then we also kind of saw at the end how kind of accounting for this heterogeneity indeed, as you'd hope, improves the statistical performance. And maybe I should say here, and is even more robust than surprisingly robust. And so please see the paper for, we've got many more details about the algorithm derivations, many more simulations comparisons. Actually, we also have some experiments on real data. So with that, thank you very much for your time and all your questions and comments. I'm happy to take any further questions.